When applying probability to many real-world situations, the probability at each stage is dependent on decisions and outcomes that were made earlier on. When this happens, we call this conditional probability. We say that a particular event, so in this case we're calling it A, is conditional on another event B if the result of B changes the probability of A occurring. A really common real-world example of this would be something like the weather. We know that if it's going to be rainy and stormy, or it's going to be cold, that usually happens in over a patch of time. It's usually cold for a few days, for example, which means that if a particular event has happened, we'll call it B, for example, it was cold yesterday, that affects the probability that it's going to be cold today. But the best way to illustrate this is with an example. Let's say we're going to play a certain game where we do two things. We toss a coin, and then based on the outcome of that coin toss, we roll a dice. Okay. Now, if we roll a heads, we're going to roll a 6-sided dice. But if we throw a tails on the coin, we're going to roll an 8-sided dice. And we win the game if we can roll a 5 or greater. So the question is, what's the probability of winning this game? Now, this problem can be worked out from probability trees. As we go along, though, we're going to develop the notation related to conditional probability. Now, with any game, it's always a good idea to draw a probability tree. So I'm going to do that. We have two stages to this. So I'm going to draw two branches to my probability. First of all, I'm going to throw the coin, and we've been told that we're thinking about whether it's heads or tails. Now, we're assuming it's a fair coin, so each of these has a probability of 1/2. Now, I should make it clear my notation here. This half, this is the probability of throwing a heads. And my tails, this is the probability of throwing a tails. Actually, I'm just rethinking here. Rather than using T, because we've already got a name for this event, throwing a heads, I'll call this H dash, or the complement of this event. Either I get a heads or a tails. This just means I don't have to introduce lots and lots of letters. So the probability of not getting heads is 2. All right. Now this is where our conditional probability comes in, because the next event is dependent on the result of that coin toss. So let's think about these each separately. So in this particular case, if I've thrown a head, then my probability of winning, okay, is going to be the probability of getting 5 or greater on a 6-sided dice. Now the probability of doing that is 2 out of 6, or 1/3. The probability of not winning, if that's happened, has to be 2/3. Now, to denote these particular things, I can't just say, this is the probability of winning, because I'm going to have a probability of winning down here as well. I need to be able to distinguish between these two things. So the way I'm going to denote that is using what we call conditional probability notation, and that uses this symbol here, a vertical bar. Now a vertical bar in probability represents a way of saying given that. Okay, so what I can do for this probability is I can say, what's the probability of winning given that I threw a heads? Well, if I got a heads the first time, then my probability of winning is 1/3. Okay, and it is important the order you do this. The probability of this is the probability I'm looking at, given that this thing's already happened. Okay, given the condition I got a heads. So this is how we write conditional probability. Similarly, the probability of not winning given I got a heads is 2/3. Okay, then when we come to our other outcomes, okay, so if I didn't get a heads, if I got a tails, I'm throwing an 8-sided dice instead. And on an 8-sided dice, the probability of getting 5 or greater is 4 out of 8, or 1/2. So the probability of winning given I didn't get heads is a half. The probability of not winning given I didn't get heads is a half, because I got 1, 2, 3, or 4. So this will be the full probability tree. Now, the other thing we should do is distinguish these events from each other. So here, the probability, this branch of the probability tree represents winning and getting H. Now I use the intersection formula here because this is like the intersection of events. Like in particular cases, if we drew a Venn diagram, let's say this is the coin toss and this is winning the game. Sometimes I'll get a heads and we'll win the game, so I'll be in here. That's what this outcome represents. Sometimes I won't win the game, but I'll get a heads, so that represents this area. Sometimes I'll get a heads and win the game, not get a heads and win the game, so that's in here. And sometimes I'll not get a heads and not get both, so it's out here. So when you see intersection, you can just read that as and. Winning happened and getting a heads happened. Similarly here, this branch of the probability tree is losing the game and getting a heads. This branch is winning the game and getting a tails or not getting a heads. And this one represents not winning and not getting heads. Now, if I want to find what the probability of winning is, that was my ultimate question in this. It's going to be looking at all the ways I can win, this way and that way, and adding them together. So what's the probability of ending up here? Well, the probability of winning and getting heads is going to be 1/2 times 1/3, which is 1/6. The probability of winning and not getting heads is 1/2 times 1/2. I shouldn't do that because that's not a probability there. Is 1/4. So the probability of winning is going to be 1/6 plus 1/4. I don't have a calculator handy, but it's good to be able to do this in our heads. So I need to get a common denominator here. So it's going to be 4 on 24 plus 6 on 24, 10 on 24, which is 5/12. And that sounds about right, slightly less than 50%, and that makes sense because I've got a 50-50 chance of getting either option. If I get a tails, should have a 50% chance of winning. If I get a heads, I've got a slightly less than 50% chance. So it makes sense that this would be overall, I'm going to lose more games than I'm going to win, and just by a bit. So that seems like the right answer. One final thing we want to get from this, and that is what we call the conditional probability formula, and it comes from this notation here, and actually specifically where we're working this bit out here. To get this probability, so sorry, maybe I'm moving a bit fast here. I'm looking at how I calculated this probability. The probability of winning and getting a heads. So think about how we calculated that. What we did was we multiplied the probability of getting heads by the probability of winning given I got a heads. So this was the probability of heads multiplied by the probability of winning given I got a heads. And if we rearrange this and make this the subject, we get the following. The probability of winning given a particular thing is equal to the probability of winning and getting heads divided by the probability of heads. Oh. And generally I'm going to rewrite this in terms of A's and B's. So the probability of a particular event happening given B, probability of A happening given B, is equal to the probability of A and B happening divided by the probability of B happening. This is what is called the conditional probability formula, and it has a lot of really useful applications.